Thank you to the organizers for the opportunity to present this work and to attend this conference. I will talk about results from a number of joint projects with Rob Clabbers, Edwin Langman, and Jonathan Monels in some combination. In all cases, what I will describe are new examples in what we call the Soliton Calogero Moser correspondence with spin. By this I mean precise relations between, on one hand, integrable PDEs or Soliton equations, and on the other, Calogero Moser systems with internal degrees of freedom or spin. In fact, this correspondence is well known, at least in the spinless case, and it can be realized in two ways. In the first way, special solutions of an integral PDE, for example soliton solutions, are shown to be governed by a complex CM system via a pole ansatz. The second way, and this is a more recent idea, is to take continuum limits of CM systems, and in doing so, generate new integrable PDEs. In fact, the PDEs found in this way turn out to be non-local, with non-localities given by a Hilbert transform or a generalization of a Hilbert transform. So today, my focus is on providing some new examples in this correspondence that involve spin generalizations of CM systems. So these are generalizations of conventional CM systems where the particles carry internal degrees of freedom, colloquially called spin. And the main result of this talk, which is also a springboard for some generalizations I will also describe, is a new equation, the spin-Benjamin-Ono equation, together with precise relations of this equation to the rational and trigonometric spin CM systems. So I've written the spin-Benjamin-Ono equation here. It's an equation for a square matrix valued function u. The curly brackets indicate an anti-commutator, the square brackets indicate a commutator, and H is the Hilbert transform. But we also have generalizations of the spin-Benjamin-Ono equation, and these generalizations are related to the hyperbolic and elliptic spin CM systems. The correspondence at the elliptic level is particularly interesting because in order to establish it, one needs a new Becklin transformation for the elliptic spin CM system. And this has some novel features that I'll have a chance to describe later in the talk. I'll start by giving an overview on Calogero Moser systems and how they're related to integrable PDEs before I focus on the spin-Benjamin-Ono equation and describe our main result on this equation. The generalizations of the spin-Benjamin-Ono equation are of intermediate long-wave type. So by this I mean they involve singular integral operators that are familiar from the theory of the intermediate long-wave equation. And here we have an elliptic integrable system that is related to the elliptic spin CM system. Towards the end of the talk, I'll say a bit about special cases and singular limits of our new equations, spin-Benjamin-Ono equation and its generalizations. And before I conclude by just providing some remarks on the results and possibilities for future work. CM systems are integrable many-body Hamiltonian systems in one dimension. and I've written their Hamiltonian here. AJ and PJ are canonically conjugate positions and momenta. G is a coupling constant, and V is a special function that must take one of 4 particular forms. So in all cases, all choices of V, you get singular long-range interactions. The long range here means that we don't have just nearest neighbor interactions, but rather this double sum runs over all j not equal to k. The possibilities for V are listed here. In fact, it's a hierarchy of possibilities, because at the top we have the elliptic case, where V is the Weierstrass P function with periods 2L and 2I delta. L and delta are free parameters, and by taking limits with respect to L or delta, we can degenerate into the hyperbolic, trigonometric, and rational cases. One very important feature of CM systems for us is that complexification preserves integrability. So if we allow AJ and PJ to be complex, which is required to make contact with integrable PDEs via this pole ansatz, that we still have integrability. And then this gives, in principle, exact solutions to the integrable PDEs if we can solve exactly this auxiliary CM system. This idea of a pole ansatz goes back to Kruskal, who argued that meromorphic solutions, for example solitons of integral PDEs, can be understood through the dynamics of their poles. Dynamics of their poles moving in the complex plane. So using this logic, it follows that, well, you can make an ansatz for the solution with some time-dependent poles in the complex plane, and this can be used to actually generate solutions of integrable PDEs. And this is borne out through many examples, but to name a few, this works for Korteweg-de Vries, nonlinear Schrödinger, and important for this talk, Benjamin Ono. So this, but in all these known examples, you make this ansatz where you have time-dependent poles moving in the complex plane, and it can be shown that in order to have a solution of the integral PDE, the poles must satisfy CM dynamics. So they must move or evolve according to the equations of motion following from the Hamiltonian I wrote on a previous slide, with possibly some constraints on the phase space. But these constraints can be understood as constraints on the initial conditions, because if they're imposed at time equals 0 under the flow of the CM system, they will be preserved at future times. This complementary approach of taking continuum limits has several interesting examples that I will mention. Here what we're doing is we're taking a limit as the number of particles goes to infinity. So n is a free parameter in these CM systems. By taking this limit in an appropriate way, you can generate equations that describe the continuum dynamics, and in known cases these are partial integral differential equations. So they're non-local equations with singular integral operators. In known cases, importantly, this preserves integrability. This approach was pioneered by Abhinav, Bettelheim, and Wiegmann, who studied a fluid of Calogero Moser particles and showed that this fluid is described by what they called the bidirectional Benjamin-Ono equation, which turns out to be equivalent, after a Madelung transformation, to a non-local version of the nonlinear Schrödinger equation. Zhao and Stone and Lensman and Shikora independently studied the continuum limit of a special case of a spin CM system, namely the rational spin CM system, and which is called the Haldane-Shastry spin chain. And they showed that the continuum limit is the half-wave maps equation, which is a non-local variant of the Heisenberg ferromagnet equation. The Heisenberg ferromagnet equation has a second spatial derivative on the right-hand side, while the half-wave maps equation replaces that with a Hilbert transform times a first Hilbert transform of a first spatial derivative. Recent work with Edwin Langman and Jonathan Monels, we studied the second quantization of the elliptic CM system. The second quantization is a kind of continuum limit at the quantum level. So we looked at the quantum version of the CM system, which is also integrable. And by taking a continuum limit, we found a new equation, the non-chiral intermediate long-wave equation. So non-chiral here essentially means parity invariant, while the intermediate long-wave equation itself is not parity invariant. What we found, this non-chiral intermediate long-wave equation is actually a variant rather than a generalization of the intermediate long-wave equation, and this will make an appearance a bit later in the talk. To summarize a bit, a pole ansatz takes us from an integrable PDE to a CM system, while a continuum limit does in some sense the opposite. We go from a CM system to an integrable, in known cases, non-local PDE. And in fact, I'll just mention that these viewpoints are closely related. So this diagram should be interpreted in a moral sense rather than in a precise way. But the paradigm is, well, you start with your CM system, you take the continuum limit, and you generate an integrable PDE. But by inserting an appropriate pole ansatz into that integrable PDE, you can arrive back at the integrable mini-body system. Perhaps not exactly the same system, perhaps some complexification has occurred, or there are new constraints on the initial condition. But this paradigm is borne out in all known examples. So I'm now prepared to say some things about spin CM systems and then show how they're related to the spin Benjamin-Onu equation. As before, I'll start by writing down the Hamiltonian for the spin CM system, which again comes in 4 species. So the new feature here is that the coupling constant G has disappeared and it's been replaced by these combinations of EJs and FJs. So it's important here to take some time to explain the notation. The AJs and PJs are, as before, canonically conjugate, and we'll let them be complex from the get-go. The EJs are what we call kets, and they live in a finite dimensional complex vector space V. The FJs are bras, and they live in the dual vector space V star. And we have this constraint between the FJs and EJs, so this juxtaposition indicates an inner product. So this is Dirac-Bra-Ket notation. So this juxtaposition of a bra to the left of a ket indicates an inner product, while the other way around indicates an outer product, which lives in the tensor product of V with its dual. We also use this notation dagger to indicate Hermitian conjugation, so this takes us between V and V star. So this is enough to define the Hamiltonian. Of course, the system is not well defined without Poisson brackets, and these would also be needed to make statements about integrability. I won't write down the explicit Poisson brackets between the FJ and the EJ, but I'll write down the equations of motion for the system on the next slide. It just suffices to say that, well, this is a generalization of the conventional CM system and it preserves integrability. So here are the equations of motion. We have expectedly is second-order Newtonian equations of motion for the AJ. In addition, we have these first-order equations of motion for the EJ and the FJ. And one thing to note is that inner product constraint between the EJ and FJ written on the previous slide is conserved just by the equations of motion for the EJ and the FJ. And this can be verified by a short calculation. So, just a reminder that this still comes in four species. We have different possibilities for V, and I'll start by considering the rational case, so where V is just 1 over z squared. And that will be what's needed to give us a relation with the spin-Benjamin-Onu equation. So I write the equation again, but now I can also write explicitly the Hilbert transform. So the Hilbert transform is a singular integral operator. The dashed integral indicates we have a principal value prescription with respect to the singularity in the integrand. And this might look a bit exotic, but one thing to note is that the Hilbert transform has a very simple representation in Fourier space. It's a Fourier multiplier by the sign of the Fourier number. Before moving on to discuss our main result here, I'll say something about the conventional Benjamin-Onu equation. So this can be recovered from the spin-Benjamin-Onu equation in the case d equals 1. D is the dimension of the matrix. In this case, the commutator vanishes. Commutator term vanishes. The anti-commutator term just becomes multiplication. And we get this conventional Benjamin-Onu equation. So this is known to be integrable. It has an inverse scattering transform, and importantly for our purposes, it has soliton solutions that are governed by the conventional CM system, rational CM system. The spin-Benjamin-Onu equation, this generalization of the conventional Benjamin-Onu equation, is also integrable, and this was established by Girard, who found a lax pair structure for the spin-Benjamin-Onu equation. What I want to communicate in this talk is the following result. The spin-Benjamin-Onu equation and a non-chiral generalization thereof, that I will write a bit later, provide a correspondence with all four species of spin-CM systems. So all four possibilities for the potential V, elliptic, hyperbolic, trigonometric, and rational. But our main result here, I'll start with the spin-Benjamin-Onu equation, is a precise relation in the form of n soliton solutions from the spin-Benjamin-Onu equation to the spin-CM system. So the result follows by inserting the following we call a spin pole ansatz into the spin-Benjamin-Onu equation. So it's a spin pole ansatz because it involves time-dependent poles moving in the complex plane, but it also involves these spin variables EJ and FJ coming from the spin-CM systems. Something to note is this juxtaposition of a ket to the left of a bra indicates an outer product. So in the numerators, we have square matrices. In fact, these are projection matrices because of this inner product constraint between the EJs and FJs. Well, our main result is the following. It's a construction of Hermitian soliton solutions of the spin-Benjamin-Onu equation. So if we have a solution of the spin-CM system on some interval with initial conditions that satisfy some constraints, namely that the imaginary parts of the poles are negative, this familiar inner product constraint between the FJs and the EJs, and this new constraint, first order equations of motion for the AJ, If these initial conditions are satisfied, then our pole ansatz with the parameters solving the spin CM system solves the spin Benjamin-Ono equation, provided that the imaginary parts of the poles remains negative, the poles do not tend to infinity, and the poles do not collide on the interval in question. So how to prove this? Well, it's mostly by direct calculation using a Becklin transformation for the spin CM system, which was already known. In addition, we use some standard arguments concerning existence and uniqueness for ordinary differential equations. But the first step is just direct calculation, using the fact that the Hilbert transform has as eigenfunctions the boundary values of those functions that are analytic in the upper or lower half planes. So doing this, one shows that the spin pole ansatz satisfies the spin Benjamin-Ono equation, provided that the following conditions hold. So we have these same constraints on the imaginary parts of the poles, this inner product constraint, this constraint involving the first derivative of aj, and then we get these familiar equations for ej, fj. These are the same first order equations for ej and fj that appear in the spin rational spin CM equations of motion. So we know under what conditions we have a solution, and then it must be shown that the equations that we've just derived, together with this inner product constraint, imply the spin CM equations of motion. So the equations for EJ dot and FJ dot are the same, but we must show that the Newtonian equations of motion for the AJ dot are implied by the first order equations on the previous slide. And in fact, the result we need to do so is known. We just need to take a certain reduction of a known Becklin transformation of the rational spin CM system, which is due to Gibbons, Hermsen, and Wojciechowski. And then after this, the result, the theorem stated on the previous slide, will follow by standard existence and uniqueness arguments for ODEs, which I won't go into the details here. So the proposition that we need a reduction of is the following. It gives a relation between certain solutions of distinct spin CM systems. So the statement is as follows. Suppose we have one set of variables, AJ, EJ, FJ, and a second set of variables, BJ, GJ, HJ, which satisfy the usual inner product constraints and also the first order rational spin CM equations of motion. So these are just the equations for the spin variables. Together with these equations, first order equations for AJ and BJ, which constitute a Becklin transformation for the rational spin CM system. So suppose all of these are satisfied, then it can be shown that both sets of variables, AJ, EJ, FJ, and BJ, GJ, HJ, satisfy distinct rational spin CM systems. And note that they can even have different numbers of particles and but we don't need the full result for our purposes. We rather just need a kind of reduction, a Hermitian reduction of this that reduces the first equation for AJ dot into that we encountered previously by inserting the pole ansatz. So we impose this reduction. We require that the number of particles for both spin CM systems be the same, and then we impose that the remaining variables are Hermitian conjugates of each other. And then the corollary is as follows. So suppose we have some variables AJ, EJ, FJ that satisfy this inner product constraint and also satisfy the first order rational spin CM equations of motion, so the equations just for the spin variables, and also this first order equation for AJ. then our variables will satisfy the full rational spin CM equations of motion, so including the Newtonian equations of motion for AJ. So then to summarize, I mean, after we have this result in place, the theorem follows by standard arguments. So we've shown that the spin pole ansatz, written again here, will solve the spin Benjamin-Ono equation, provided that the parameters therein solve the rational spin CM equations of motion, subject to certain constraints that were written before. So this is the first instance of a Soliton spin CM correspondence that I can present today, but there are now several interesting generalizations of this result that I will describe. The first of these is fairly straightforward. We had a relation from the spin Benjamin-Ono equation to the rational spin CM system, and it's not hard to also get a relation to the trigonometric spin CM system. So this is done by considering 2L periodic solutions of the spin Benjamin-Ono equation. And if you do this, instead of looking at the spin Benjamin-Ono equation on R, you can look at it on a circle, and in that case the Hilbert transform takes a different form, kind of an obvious trigonometric variant of the Hilbert transform, where you replace the rational kernel by a cotangent kernel. The following result is established completely analogously to the previous one. If we make a spin pole ansatz for the periodic Benjamin-Ono equation, so this is written at the top with the periodic Hilbert transform, here alpha is this cotangent function, and HC indicates Hermitian conjugate, it can be shown that this will solve the periodic spin Benjamin-Ono equation, provided the parameters in the pole ansatz solve the trigonometric spin CM equations of motion, subject to constraints which are analogous to those in the rational case on the previous slides. More interesting, though, is if we can somehow obtain a relation to the hyperbolic and elliptic spin CM systems. But to do this, we actually have to generalize the spin Benjamin-Ono equation. So that will be our next task. In doing so, we can look for guidance. We can think about how to generalize the conventional scalar Benjamin-Ono equation. And there are basically two ways to do this. The first is to replace the Hilbert transform with a hyperbolic generalization of the Hilbert transform called a T-transform. So this gives the intermediate log-wave equation, which is a very interesting equation in its own right. It has a free parameter delta coming from this T operator, and by taking limits with respect to delta, we could recover both Benjamin-Ono and KdV in different limits. A second approach, and we know this from recent work with Edwin Langman and Jonathan Linnells, is that there's a way to replace the Hilbert transform with a matrix operator. I call this matrix T, and I'll give some details on what this means on the next slide. And this is more natural from a pole ansatz perspective, or trying to find relations to CM systems. Essentially, it has to do with the fact that this matrix T operator has eigenfunctions, while the conventional T operator does not. And this is very nice and very useful from a pole ansatz perspective. But I'll describe what we get when we apply both approaches to our spin Benjamin-Ono equation. So the first approach, replacing H with T, leads to what we call the spin ILW equation, or SILW equation. and it's written as follows. It's just the Benjamin-Ono equation with t replacing h. And I've written the definition of t here. It's kind of an obvious hyperbolic generalization of the Hilbert transform. I've also written the periodic version of the t transform here, and this is where things start to get a bit interesting because we see the emergence of elliptic functions. So zeta 1 is a minor variation of the Weierstrass zeta function that's needed for our purposes. In fact, it's periodic in the real direction. But I won't write down the precise definition. We don't need it. This periodic operator will make an appearance a few slides later, but now I want to think about what we get from this second approach, generalizing the spin Benjamin-Ono equation. So we get what we call the non-chiral Silw equation, or the spin non-chiral intermediate long-wave equation. So this is a two-component equation. It involves two matrix-valued functions u and v, and two integral operators t and t tilde. So t is as before. T tilde is an integral operator, but it's not like t a singular integral operator. It has a non-singular kernel. So the point, one important point, is that we can equally well write this two-component system in a matrix notation using this matrix T operator, which is composed of T's and T tildes. I won't do this because we don't need it for the talk. But in doing so, you can write the SNC-ILW equation in a form that's very similar to the spin Benjamin-Ono equation, and many of the pole-ansatz calculations go through fairly straightforwardly. In fact, we can, without too much trouble, establish a completely analogous result for the SNC-ILW equation, that it has soliton solutions that are governed by the hyperbolic spin CM system. But this is not so interesting. What I'd rather talk about is the elliptic case, where things become very interesting. We really have new features going on in the elliptic case. So the elliptic case, I mean the periodic version of the SNC-ILW equation, which involves these integral operators that themselves involve elliptic functions, and ultimately where we'll be able to make a correspondence to the elliptic spin CM system. So this is the two-component system we'll consider, and these are the corresponding periodic operators. Again, zeta 1 is a minor generalization of the Weierstrass zeta function, but the precise form is not important for what follows. Our main result on this equation is that it admits a class of periodic elliptic solutions that are governed by the elliptic spin CM system. So to establish this result, we again use a pole-ansatz. But this pole-ansatz we use is rather different, or has one very different new feature versus the degenerate cases. So this is the pole-ansatz for u and v. Alpha is a special function zeta 2, again a minor generalization, a minor variant of the Weierstrass zeta function whose precise form is not important. HC indicates Hermitian conjugate. What's new here is the presence of this m. For both u and v, we have this term mt. We call this a background matrix, and its presence is essential to make the pole-ansatz consistent. In fact, it's also essential that it's dynamical to make the pole-ansatz consistent. And this is very different from degenerate cases. And the necessity of the m actually could be traced back to the fact that the Becklin transformation for the elliptic spin CM system, which is not known before, this is a result of our work, requires this M in order to mediate the transformation between solutions of two distinct spin CM systems. So to give a bit more details on the results, we're able to show that U and V from the pole ansatz before satisfy the periodic SNC-ILW equation provided that the parameters solve the elliptic spin CM system subject to certain constraints which are analogous to those before, and additionally the following conditions are met. So here Pj is a shorthand notation for the outer product of Ej and Fj. So we require that M evolves according to this first order equation of motion, which only involves the Aj's, Ej's, and Fj's. And we have some constraints on M itself, so namely the sum of Pj minus the summation conjugate, sum over J, must be 0. And this is a constraint on initial conditions. If this is satisfied at t equals 0, it will be satisfied at future times. I should note that this special function kappa 2 that appears in the time evolution equations for M, well, this is an elliptic type function given by zeta 2 squared minus p2. P2 is a minor variation on the Weierstrass p function. So this is the result, but in addition to giving us special solutions of the periodic SNC-ILW equation, we found we found a new Becklin transformation for the elliptic spin CM system with some novel features. So it's interesting to spend a bit of time on this. I've written the Hermitian reduction of the elliptic spin CM system here. And the new feature, again, versus the degenerate cases, is this first term, which involves this dynamical background matrix M. And of course, to have the full Becklin transformation, you need the equations on the previous slide. So the time evolution equation for M, the constraints on the Ej and Fj, and actually the equations of motion for Ej and Fj as well. So I'll just emphasize there are fundamental differences versus both the degenerate cases, which we've already seen. They don't have this M. In fact, you can insert it, but it wouldn't be dynamical. So this is a difference. But also there's very interesting differences versus the scalar case. So the Becklin transformation for the elliptic conventional CM system. In that case, you have what's called a balancing condition, and this means that the Becklin transformation can only relate CM systems with the same number of particles. So you must have n equal to m. Here, in the spin case, we can have n and m not equal, but we have this condition on the pj's, equivalently a condition on the ej's and fj's at t equals 0, which is new. So how did we know how to do this? Well, actually, this what I've just described is kind of a generalization of recent work with Rob Klabbers on working this out in a special case, actually a singular limit of the SNC-ILW equation called the Non-Chiral intermediate Heisenberg ferromagnet equation. So the details are in this preprint I've given. Okay, so to summarize a bit, we have this pole ansatz that takes us from spin Benjamin Ono to rational or trigonometric spin CM, and also takes us from SNC-ILW to either hyperbolic and elliptic spin CM. So I had this diagram at the beginning of the talk that suggested that this is really a two-way street. We should also be able to take limits of the spin CM systems and somehow get out these equations we've already found. But this is left to future work. We don't have this result yet, but we would anticipate it. So I'll say a few things about limits and special cases. here's the spin-Benjamin-Ono equation again. So by inserting a particular form for u written here, so rho is a scalar function of x and t, m is a 3-vector function of x and t, and this bolded sigma is the poly 3 vector, we obtain this rather unwieldy system of equations. But this is very interesting because we can take limits of this fairly complicated system and recover both the Benjamin-Ono equation and the half-wave maps equation. I mentioned this at the beginning of the talk. This is a non-local variant of the Heisenberg ferromagnet equation. So one way of thinking about this spin-Benjamin-Ono equation is as an integrability preserving hybrid of the Benjamin-Ono and half-wave maps equations. If we look instead at the Silw equation, so this made a brief appearance as one way to generalize the spin-Benjamin-Ono equation. Well, this involves this t operator which has a free parameter delta. And by looking at the behavior of t acting on a derivative as delta goes to 0, we can compute different limits of this Silw equation. So by different rescalings of the dependent variable, we can get different delta to 0 limits actually. One of these is perhaps expected. It's the matrix KdV equation, which actually goes back to Lax in his famous paper. But what's interesting is that we can also get the generalized Heisenberg ferromagnet equation out in a different delta to 0 limit, so a different rescaling of the dependent variable. And this can be reduced to the conventional Heisenberg ferromagnet equation. So I will just summarize now. The spin-Benjamin-Ono equations, spin-Benjamin-Ono and spin-NCILW equations, together with their periodic variants, can be linked to all 4 species of spin-CM systems. And, well, 3 of these are straightforward, but the elliptic case is quite a bit more interesting, involving some new features coming from the novel Becklin transformation. And I've also briefly shown, just a few slides back, that the spin generalizations of Benjamin-Ono and ILW equations we found actually contain several known integrable systems as special cases or singular limits. As for future work, well, we are hopeful that the spin-Benjamin-Ono equation could provide a kind of prototype of integrable spin hydrodynamics. So it involves coupling of spin and density degrees of freedom, which, well, we're not aware of integrable models with this feature, and it would be interesting to explore this further and try to relate this to a spin CM fluid. So seeing if this could be realized as a continuum limit of a spin CM system. The quantum picture is very interesting. So the Benjamin-Ono equation can be understood as coming from a second quantization of the rational, or rather trigonometric, conventional CM system. And so it would be reasonable to expect that the spin Benjamin-Ono equation could be understood as coming from a second quantization of the spin CM model. One possibility for generalizing or extending our results is to look at Reuschner-Snyder, so relativistic generalizations of CM systems, and seeing, well, what kind of soliton equations do these correspond to, particularly in the spin case. So thank you for taking the time to listen to my talk.